week we have been talking about Kramer-Rao bound. So as we have mentioned, we have many considerations for a parameter estimation. The major thing is we will ask some questions, right, at the beginning. The first question is it unbiased? Meaning that if you take the expectation for the estimator, would it be equal to the true value? If yes, then that is unbiased. And something unbiased, that is good, right? It's something we like to have. And if it's biased, then we sort of unhappy about it, right? Okay, then the next thing is how much deviation would it be from the true value? And that will be measured by the variance, or to be more accurate, we should say MSE, minimum mean square error, the mean square error of the estimator. That would be the key point for our for the performance measurement for the estimator. Okay, so then we come to the point of this CRB, this CRB. So we are at the page 30. If you like to follow, then you can go to page 30 and then follow the textbook to read with this video explanation. So regularity condition, which means that at the at some values it will not be something like it need to be flat at the mountain. So meaning that it's deliverable. You can take a derivative of it. You know, some derivative does not exist for some function. So what that means is it exists and it's equal to 0. Okay, and then the variance of any unbiased estimator would be larger than this equation. Then if we take a detailed look at the equation, it will be the likelihood function, take the second order derivative with respect to theta and take the minus sign. And that would be it. Okay. If you read up to this point, that would be the CRB. That would be the CRB already. Then uh, the next thing is there are some additional properties. An unbiased estimator may be found that attains the bound for all theta if and only if. Notice this, if and only if. If and only if this exists, meaning that if you take the derivative, then it can be formulated into I of theta multiplied by g. The point is this g function does not have theta in it. Theta is completely moved out of x. You notice this. Please notice that the theta does not exist here. It's moved out of this function. So in some in some perspective, we will say that theta is actually separable. It's separated from theta. So that's what it means. Then that I is visual information. Visual information. Then the minimum variance would be 1 over I of theta. Then the expectation is given by this one. Okay. And then we have an example. I'm going to go through it quickly. So this is a sample mean example. So you take the variance of sample mean. If you don't remember, you can go back and check example 3.1. So this is the example for the sample mean. We are trying to take the sample mean and to estimate that A had. Alright, so uh, it has to be larger than sigma squared for all A. Okay, so let's go to the next page. So no unbiased estimator can exist whose variance is lower than sigma square for given a single value of A. But in fact, we know that if A is equal to this, then it's sigma square. So if we take A had to be equal to that, it it is sigma square, which is exactly the CRB. As a result, this estimator seems to be unbiased and it attains CRB. So now what can we say? We will say this is good because it unbiased and attains CRB. So we're happy about it. Okay, then there are some arguments about this. And if you let theta equal to A, and so on and so forth, I'm going to just skip part of it. All right. So, and then the other example is DC level in white Gaussian noise. So you will have X equal to A plus Wn. Then you try to take the likelihood function, which is written in this way. We have talked about this in the previous class, so I'm going to through quickly. Uh, then take the first order derivative, you get something like this. And then you take the second order derivative. Take the second order derivative. And then we come back a little bit. You see, you second order derivative, take the expectation and take the minus sign and put it in the denominator. That would be the CRB. So that's exactly what we do here. We take the negative sign and put it at the denominator, which is sigma square over n. Then that would be CRB, right? And but the point is, if you take the sample mean, if you take the sample mean, you get the variance of sigma square over n. So as a result, A hat, if you just take the sample mean as the A hat, that would be sufficiently good because it just attains the CRB. Okay, so we can prove it's attained. Okay, so but you take the variance of this is equal to this, and I is equal to this. This is by definition. This is by definition. Then VAR for this is also by our CRB equation in previous page. Right? And then you take the first order derivative, which can be equal to I theta hat minus this. Differentiating the later produces this. Right? You take this, the take derivative of this one more time, and then you get something like this. Taking the negative expected value. How come? Notice that. Notice here. We are doing this. So take the negative, and expectation. You get something like that. And because this is unbiased, if something is unbiased, you take the expectation, and minus theta is supposed to be 0. So here we get 0, and then I of theta remains. And therefore, we get something like this, because you put this in the denominator. So that CRB is attained. But in some cases, the CRB will not always be satisfied. So this is not trivial. Okay, but I'm going to just skip this and maybe leave it for your practice later. So the whole paragraph explains what happens here. If you have variance, you have a variance and versus theta. You might have theta 1 that consistent with CRB, and you have theta 2, you have theta 3, then at the end, what can you say? You will say theta 1 is better because it's uniformly better all over the area compared with the other two person, right? So you will say theta 1 is definitely better. And in this case, theta 1 is still better, but it does not attain CRB. In that case, you can still say theta 1 is better than theta 2 and theta 3. But you no longer say theta 1 is optimal because there might be someone, maybe theta 4, theta 5 exists in this area that gives better performance than theta 1. It is possible, right? So until you reach CRB, you cannot say there is no better one unless you prove it. Otherwise, there are always some space here. Then that would be the thing, the property. You will not be able to claim that. Okay. And here we formally define feature information I theta. This is invented by a statistical mathematician called, his name is Fisher, and it's maybe more than 100 years ago. Statistical person, mathematician, yeah, whose name is Fisher. So it's named after his. Uh, it would define I theta as log likelihood take second order derivatives, two order derivative, and take the expectation and then minus sign. That would be I theta. And but if you just put it at the denominator and put a minus sign on it, minus meaning plus. So you get variance of theta larger than this. That's the lower bound. Okay. And the point is, it has essential properties of an information major, has some essential property. The first property is non-negative. It should not be non-negative, right? If you say you find some information major that is negative, how come it's wrong? What's wrong about a negative information major? If an information major is negative, you can just not using it, right? You don't use it, then you get zero information. As a result, negative information means something ridiculous, right? Because for this measurement to be negative information, you can just discard it. You don't have to use it. Then you get zero information, which is better than using the information, right? So as a result, when we measure information, it has to be positive. Or at least it will be zero. It should not be negative. So it's non-negative. And then for independent observations, you are going to expect additive property. How come? Think about it. Think about it. If you have two samples, you are expecting twice as much information as if you have one sample, right? If you have two samples, you are expecting twice information. The amount of information should be twice. Not 1.5, not 1.8, not 1.2, but just 2, right? Additive, additive. So that's very important concept. And visual information, the, the definition of here, visual information, it would satisfy this property we expect it to have. Notice that as for an information major, there are a couple other definitions by other statistical mathematicians, but visual information is the most common one and is most acceptable one. So we talk about this, but we don't talk about others. But if you check carefully, you will find other definitions about information major. Okay, so the latter property leads to the result that the CRB for IID observations 1 over n times that for one observation. So, for example, if we have independent observations like this, x, notice that x is what? It's a vector. We have multiple samples. Notice that we have multiple samples. So As a result, for these multiple samples, we have 1, 0 to n minus 1. And their likelihood can be, because they are independent, it's very important that it's independent. Because just because it's independent, then you can put it into multiplications, right? They are p of x1 multiplied p of x2 multiplied p of x3 multiplications. And those multiplications, when they are in Ln natural log, it, it will turn into a summation of log. So you see, this is a vector, then it turns into summation of Ln p of this thing, n from 0 to n minus 1. As a result, if you have put this into here, notice that just follow the process. Beware to follow a process. You go from there, here to there, and then this thing is summation. And that summation inside can be taken out. So as a result, you have summation of this. So as a result, what you see here is you have information measure for one sample and then sum it all together. As a result, what can you see? You see visual information of theta equal to n times small I. Small I is the information for one sample. This is the information for n sample. Then the n sample information is n times I, small I. That's reasonable, right? You have n sample as opposed to one sample. Then you get n times the information. Reasonable, right? It's like, think about this. You work for 1 hour, you make $1. If you work 10 hours, then you expect you get $10, right? This is what it means. You have 10 samples, then you get 10 times the information. Reasonable. That's reasonable. Okay? But and that there is nothing sophisticated here. This is just the information for one sample. For one sample. Okay? So for one sample, for non, then the point comes here. For non-independent samples, what will happen? Think about this for a minute. What is going to happen if the sample is not dependent? It's not independent, which means that it's independent. It's dependent. If something is dependent, we will expect the information will be less than ni theta. How come? One thing to do is you go through the derivation. This would not be able to be written in the summation form. All right, that's something to think about. One direction. The other direction is if samples are correlated, they sort of duplicate each other. So as a result, you have 10 samples. The information is not 10 times. It will be less than 10 times. Because some of the information are redundant. They're correlated, they're redundant. Then as a result, information will be less. Okay, so conceptually that would be one way to explain it. For completely dependent samples, for example, if all the samples are the same, we'll have I, capital I, theta equal to lowercase I. So you have n samples, and the amount of information is just exactly equal to one sample because they are completely redundant. They are all the same, completely dependent and redundant. Okay, so that would be the case. Okay, that would be the case. And conceptually, if things are redundant, they're not that good, right? Okay. So additional observations carry no information because you're observing this dependent samples. If they are disturbed by noise, they are disturbed by the same noise. If they are disturbed by some interference, they are disturbed by the same interference. As a result, they carry no information. And then CRP will not decrease. Okay, I think that's the uh, let's take a brief break and we'll come back soon.